Hi, I'm Alex. We're facing a question so deceptively simple that it dismantles the way the human mind understands numbers, distance, and meaning. How many stars exist in the universe? The answer lives far beyond intuition, beyond ordinary scale, and somewhere between mathematics and awe. This journey won't just give you a number, it will change how you see the sky above you. If you'd like to return for more journeys like this, a quiet subscribe helps keep them unfolding. Now let's begin. 200,000, 1,000, dollars. 200 billion trillion. That's the number of stars in the observable universe. And your brain just refused to process it. I know it did. Because every human brain does the same thing when confronted with numbers this large. It accepts the information intellectually, but it cannot feel what that number means. You can't picture it the way you can picture 5 people standing in front of you. Try to think about it. Really think. Do you feel it, or do you just know it's big? Tonight, you're going to look up at the night sky and try counting stars. Maybe you'll get to 30. Maybe 50 if you're patient, maybe 100 if you're really determined. And then you'll give up. Not because you're lazy, because your brain literally cannot continue. It hits a wall around 15 to 20 objects, and everything beyond that becomes fuzzy estimation rather than actual counting. This limitation isn't a failure of intelligence, it's how human cognition evolved. Walk into a dark bar right now, and your brain automatically assesses how many people are there. 5 people. 10, your estimate is probably spot on. 20 people, still pretty good. But push it beyond that, and things get weird. Is it 40 people? Or 60? Most of us genuinely can't tell without counting. Our ancestors needed to assess immediate threats and opportunities. How many predators are approaching? How many members of my tribe? How many animals in that herd were hunting? These numbers rarely exceeded a few dozen. We never evolved the mental machinery to intuitively grasp thousands, let alone millions or billions. When someone tells you a stadium holds 70,000 people, you accept it intellectually, but you don't feel what 70,000 means. Here's where it gets interesting. In 1974, researchers at Harvard conducted an experiment. They showed people photographs for half a second. When the image contained 4 black dots, participants identified the quantity instantly and correctly 100% of the time. When the image contained 40 dots, they could only guess randomly. The brain's counting mechanism simply shut down. This creates a psychological effect that Stalin allegedly observed. 1 death is a tragedy. 1 million deaths is a statistic. Your brain processes the emotional weight of 1 person dying, but a million, a billion, the numbers become meaningless. Your brain refuses to scale the feeling appropriately, and this creates a massive problem when we start talking about stars. Because the numbers involved are so fantastically large that they exist completely outside our intuitive understanding. To count 200 billion trillion stars, we first need to hack our brains. We need to teach them to feel the difference between a million, a billion, and a trillion. There's a way to do this. It's called the time machine. 1,000,000 seconds is 11 and a half days. You could imagine taking an 11-day vacation. It's a long time, certainly, but it's conceivable. You can picture devoting 11 days to a single task. It's a marathon, but humans run marathons. A billion seconds is 32 years. Think about that. If you started counting the moment you were born and never stopped to sleep, eat, or rest, you'd reach 1 billion in your early 30s. The entire span from infant to adult would be consumed by this single task. What seemed like a big number with a million has become something that spans a human lifetime. Your entire youth, your education, your relationships, your career, all of it happening while you count. A trillion seconds is 31,700 years. To count that high, you'd need to have started before the invention of agriculture, before writing, before civilization itself. You'd have been counting when humans still lived in small nomadic bands, hunting woolly mammoths during the last ice age. Every empire that ever rose and fell happened while you counted. Every war, every peace treaty, every technological innovation, from the wheel to the iPhone, occurred during your count. The pyramids were built. Rome conquered the world and collapsed. The Renaissance happened. 2 world wars came and went, and you still wouldn't be finished. The difference between a million and a billion is 1,000 times. The difference between a billion and a trillion is another 1,000 times. These aren't just bigger numbers. They're different categories of magnitude entirely. From the moment you were born until right now, about 1 billion seconds have passed. Your entire life, every memory, you have every experience you've accumulated, every relationship you've built, equals 1 billion ticks of the cosmic clock. Your brain with large numbers is like me with IKEA assembly instructions. I look at them, nod thoughtfully, and then proceed to completely ignore them. Now you have a feeling for billions and trillions. So what the hell is 200 billion trillion? Picture the darkest night of your life. You're far from any city, miles from the nearest street light. No light pollution bleeding into the sky. No clouds obscuring your view. You've been sitting in complete darkness for 30 minutes, letting your eyes fully adjust to the night. The stars emerge, gradually more and more of them appearing as your pupils dilate to their maximum width. The Milky Way stretches overhead like a river of pale light flowing across the entire dome of the sky. You start counting stars, one by one, methodically working your way across constellations. How many can you see? On a truly dark night far from civilization, with perfect atmospheric conditions and exceptional eyesight, the human eye can see between 2,000 and 5,000 stars. Let's be generous and say you can see 4,000. That's the absolute maximum under ideal conditions. 4,000 points of light scattered across the entire celestial sphere. Here's the first secret the night sky keeps from you. Every single one of those 4,000 stars exists inside the Milky Way, not scattered throughout the universe, not distributed across different galaxies. All of them, every single point of light you can see with your naked eyes, belongs to our home galaxy. You're not looking at the universe. You're looking at your cosmic neighborhood. Here's the second secret. They're all close neighbors. Relatively speaking, they're practically on your doorstep. Most of the stars you can see without a telescope are within a few hundred light years of Earth. The farthest star, visible to the naked eye, is about 16,000 light years away. In a galaxy that spans 100,000 light years, you're seeing an incredibly tiny local bubble. You're standing in the middle of something vast, and you can only see the immediate vicinity. The Milky Way is what astronomers call a barred spiral galaxy. Picture a massive rotating disk with a dense bar-shaped region cutting through the middle. From the ends of this central bar, spiral arms curve outward, sweeping through the disk like cosmic pinwheels, frozen in a slow rotation that takes hundreds of millions of years to complete one revolution. Our sun sits in one of those spiral arms about 26,000 light years from the galactic center. We're in the suburbs far from the dense downtown core, where stars are packed far more tightly together than in our region. That distance of 26,000 light years translates to roughly 153 quintillion miles. The number is so large, it becomes meaningless. But it tells you one thing clearly: we're nowhere near the center of our own galaxy. The Milky Way measures 100,000 light years from edge to edge. Think about what that means. Light traveling at 186,000 miles per second takes 100,000 years to cross our galaxy. In 1 year, light covers about 6 trillion miles. Multiply that by 100,000. That's the width of our home. It's a disk of stars so vast that light, the fastest thing in the universe, takes 100 millennia to traverse it. And how many stars does this galaxy actually contain? Astronomers estimate between 150 billion and 250 billion stars. Most calculations cluster around 200 billion suns, most of them smaller and dimmer than our own, scattered throughout this massive disk of matter and light. Now let's do the shocking calculation. You can see 4,000 stars on the darkest night with perfect conditions, but they're swimming in a sea of 200 billion stars you cannot see. For every star visible to your naked eyes, there are 50 million invisible ones. 50 million. The ratio is almost incomprehensible. The galaxy is so much more densely populated than the night sky suggests that the visible stars are basically a rounding error. If your eyes could somehow see red dwarf stars, the most common type of star in the galaxy, the entire character of the night sky would change. Red dwarfs make up about 70 to 75% of all stars. They're small, cool, and incredibly faint. Despite being the most numerous stellar type in existence, not a single red dwarf is visible to the naked eye. If you could see them, the sky would be packed with thousands of stars, where you currently see dozens. The darkness between the familiar constellations would fill in with more and more points of light until the entire sky glowed with a crowded stellar field. When you see that faint band of light stretching across the sky on a dark night, that milky glow that gives our galaxy its name, you're looking edge on through the disk. You're seeing the combined light of millions of stars, too distant and too dim to resolve individually with your eyes. They all blend together into a soft, luminous river flowing across the heavens. Millions of stars compressed into that gentle glow, each one a sun like ours, separated from us by thousands of light years. You're seeing less than 1% of our galaxy's total volume. Think about it like this. Imagine standing in the middle of a dense forest and trying to count all the trees. You can count the nearby trees fairly easily. 10 trees, 20 trees, maybe 50 if you're patient. But distant trees are hidden behind the ones closer to you. The forest extends in all directions, beyond what you can see, and you have no idea how many trees exist in the parts you can't observe. That's our situation with the Milky Way. Dust clouds block our view in many directions. When you look toward the galactic center, you're peering through thousands of light years of interstellar dust. It's like trying to see through dense fog. The light from distant stars gets absorbed and scattered before reaching us. We can map the galaxy using radio waves and infrared light, which penetrate dust better than visible light. But direct observation is limited. Here's a timeline to help you truly understand 200 billion. If you started counting stars at 1 per second, never stopping to sleep, eat, or rest, it would take over 6,300 years to count all the stars in the Milky Way alone. Over 6,300 years. Let that sink in. You'd need to start counting around the year 4300 BCE. That's before the pyramids were built, before the great civilizations of antiquity emerged. You'd be counting when humans were just beginning to develop agriculture and settle into permanent villages. No written language existed yet, no cities, no empires. You start counting 1, 2, 3, 4. You continue for 4,000 years. The pyramids rise in Egypt. You keep counting. The Sumerian civilization emerges in Mesopotamia, invents writing, builds the first cities. You keep counting. Babylon flourishes and falls. You keep counting. The great Chinese dynasties rise and fall, building walls and canals and vast empires. You keep counting. Rome conquers the Mediterranean world, rules for centuries, and collapses into fragments. You keep counting through the Middle Ages, through the Renaissance. The Maya build their pyramids in Central America. The Aztec Empire rises. Columbus crosses the Atlantic. The Industrial Revolution transforms human civilization. 2 world wars devastate the planet. The internet connects humanity. Smartphones put computers in every pocket, and you're still counting. You won't finish until sometime around the year 7300. Every civilization you've ever heard of, every empire that rose and fell, every war, every peace, every technological achievement, from the invention of writing to artificial intelligence, all of it happens during your count of just the stars in our galaxy. And you still wouldn't be done. The Big Dipper that guided your ancestors across oceans and deserts for thousands of years. That familiar pattern of stars that helped sailors navigate and travelers find their way. It's floating in an ocean of 200 billion other stars that your eyes will never ever see. Those 7 bright stars are swimming in an invisible sea of stellar fire. 200 billion stars. It sounds enormous, doesn't it? It is enormous. It's incomprehensibly large. But here's the thing that's about to break your sense of scale all over again. The Milky Way is just one neighborhood, one galaxy among many. In 1923, one man discovered just how wrong we were about the size of the universe. Before 1923, humanity believed the universe was the Milky Way, and the Milky Way was the universe. That was it. Everything that existed, every star, every nebulous cloud of gas, every celestial object, all of it belonged to our galaxy. The entire cosmos, as far as anyone knew, was contained within the Milky Way's 100,000 light-year span. Astronomers saw fuzzy patches through their telescopes. They called them nebulae, from the Latin word for cloud. Some glowed with their own light, others were dark, blocking the light of stars behind them. The prevailing assumption was that these nebulae were all gas clouds within our galaxy. Some were planetary nebulae shells of gas puffed off by dying stars. Others were star-forming regions where new stars were being born from collapsing clouds of hydrogen. And some, everyone assumed, were just diffuse clouds of gas and dust scattered throughout the Milky Way. No one had any reason to think otherwise. The tools to measure their true distances simply didn't exist yet. The Andromeda Nebula had been known for centuries. It's visible as a faint, fuzzy smudge to the naked eye on dark nights, appearing as a small oval patch of light in the constellation Andromeda. Through telescopes, it looked like a spiral cloud, beautiful and mysterious, but still just a nebula, just another gas cloud somewhere in our galaxy. Persian astronomer Abd al-Rahman al-Sufi described it in 964 CE as a small cloud. Charles Messier catalogued it in 1764 as M31, the 31st entry in his catalog of objects that weren't comets. But no one knew what it really was. Then Edwin Hubble changed everything. In 1923, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest telescope in the world at that time, Hubble was photographing Andromeda when he found something extraordinary, a Cepheid variable star. This discovery might not sound revolutionary at first. You might be wondering, what's so special about finding one star in what everyone thought was a nebula? But this single star was the key that unlocked the true scale of the universe. Cepheid variables are pulsating stars with a special property that makes them incredibly useful for measuring cosmic distances. They brighten and dim in a regular, predictable cycle. Some pulse every few days, others take weeks or months. But here's the crucial discovery made by astronomer Henrietta Leavitt in 1912. The time it takes a Cepheid to complete one pulsation cycle is directly related to its actual intrinsic luminosity. The relationship is precise and reliable. Measure how long the pulsation period is, and you know how bright the star really is. Not how bright it appears from Earth, but its true brightness, the amount of light it's actually pumping out into space. It's like having a light bulb with its wattage written on the side. Once you know the true wattage, you can estimate distance based on how dim it looks. Compare that true brightness to how bright the star appears from Earth, and you can calculate how far away it must be. The dimmer it looks compared to its true brightness, the farther away it must be. It's the cosmic equivalent of the inverse square law, double the distance, and the apparent brightness drops by a factor of 4. When Hubble did this calculation for the Cepheid variable star he found in Andromeda, he got a result that shocked him. The star was roughly 900,000 light years away. His initial measurement was actually off by a factor of about 3 because the relationship between pulsation period and luminosity wasn't perfectly calibrated yet. We now know Andromeda is actually about 2.5 million light years distant from us. That's roughly 14.7 quintillion miles, or 23.7 quintillion kilometers. But the precise number didn't matter at that moment. What mattered was the order of magnitude. Whether it was 900,000 light years or 2.5 million light years, One fact was absolutely undeniably clear: Andromeda couldn't possibly be inside the Milky Way. Our galaxy is only 100,000 light years across. An object 900,000 light years away, let alone 2.5 million, was completely outside our galaxy, far beyond its boundaries. Andromeda wasn't a nebula within the Milky Way. It was an entirely separate galaxy, an island universe unto itself, a whole other collection of hundreds of billions of stars existing across an enormous cosmic distance, completely separate from our own galaxy. The universe in that single moment became incomparably, unimaginably larger than anyone had conceived. The Milky Way wasn't the universe. It wasn't even close. It was just one galaxy, among many, perhaps among countless others. The implications made astronomers' heads spin. If Andromeda was a separate galaxy, then all those other fuzzy, spiral nebulae might be galaxies too, and they were. Once astronomers understood what they were looking at, once they had the tools to measure distances to these objects, they found galaxies everywhere. Point a telescope at any patch of seemingly empty sky, and you'd find them. Dozens, hundreds, sometimes thousands. The universe was absolutely filled with galaxies. But how many galaxies existed in total? And how many stars did all those galaxies contain? For decades, astronomers could only estimate. The numbers kept growing as telescopes improved and surveys went deeper, but the true scale remained elusive. Then in 1995, astronomers decided to conduct an audacious experiment. They would point the Hubble Space Telescope, the most powerful optical telescope ever built, at a tiny patch of seemingly empty sky and stare at it for as long as necessary to capture every faint photon of light. They chose a small area in the constellation Ursa Major. This patch appeared completely empty to the naked eye. Even through ground-based telescopes, it looked like nothing. Just darkness. Just a random, boring piece of empty sky. The area was so small it could be covered by a grain of sand, held at arm's length against the night sky. Hubble stared at this empty patch for 10 days straight. 10 days of continuous exposure, collecting every photon of light that reached its mirrors. The telescope was gathering light from objects billions of times fainter than the human eye can perceive. Light from galaxies so distant, their photons had been traveling through space for most of the history of the universe. The resulting image was called the Hubble Deep Field, and when astronomers saw it, they realized everything had changed again. In that tiny, supposedly empty patch of sky, Hubble found approximately 3,000 galaxies, 3,000 complete galaxies packed into a region you could cover with a pinhead held at arm's length. Most were spiral galaxies, like the Milky Way or Andromeda. Others were elliptical galaxies, smooth blobs of stars. Some were irregular, chaotic collections, without clear structure. Many were incredibly distant, their light stretched into the red by cosmic expansion, indicating they were billions of light years away. Their light had been traveling since the universe was young. The math became simple but staggering. The entire celestial sphere, the complete sky as seen from Earth, requires approximately 12 million such tiny patches to cover it completely. If there are 3,000 galaxies in one random patch, and you need 12 million patches to tile the whole sky, that suggests tens of billions of galaxies minimum in the observable universe. astronomers pushed deeper. The Hubble Ultra Deep Field, an even longer exposure of an even smaller patch, found about 10,000 galaxies. The Hubble Extreme Deep Field pushed to the absolute limits of the telescope's capabilities, finding galaxies so distant and so faint they were barely distinguishable from background noise. Each survey found more galaxies that previous observations had missed. In 2016, a team of astronomers analyzed all available Hubble data along with observations from other telescopes. They carefully accounted for populations of faint, small galaxies that earlier surveys had been unable to detect. They corrected for the portions of the sky that hadn't been surveyed as deeply. They ran statistical models to estimate how many galaxies existed beyond what even Hubble could see. Their conclusion: approximately 2 trillion galaxies exist in the observable universe. 2 trillion, 2,000 billion, each one a collection of hundreds of billions of stars. That empty patch of sky you casually glance past every night without a second thought. It contains thousands of galaxies your eyes cannot possibly see. Each one of those galaxies contains hundreds of billions of stars. Each one is a Milky Way-sized collection of stellar systems existing across incomprehensible distances, and you can't see any of them without a powerful telescope. Hubble looked at what everyone thought was nothing and found 3,000 galaxies. It's like opening your refrigerator, expecting it to be empty because you forgot to go shopping, and instead discovering an entire supermarket has somehow been crammed inside. The empty space wasn't empty at all. It was full beyond imagination. And this is where this story completely escapes the bounds of anything that could be called normal mathematics or reasonable numbers. 2 trillion galaxies, each galaxy averaging approximately 100 billion stars. You know what happens next, don't you? You know where this calculation leads. 2 trillion galaxies multiplied by 100 billion stars per galaxy equals 200 billion trillion stars. Let me write that number out for you so you can see what we're actually talking about. 200 billion trillion is 200,000. That's a 2 followed by 23 zeros. In scientific notation, it's 223. Your brain just did that thing again, didn't it? It accepted the number intellectually, while completely failing to grasp what it actually means. And honestly, that's fine. No human brain can truly comprehend a number this large, but we can try to find comparisons that at least gesture toward the magnitude. There are approximately 7.5 quintillion grains of sand on all of Earth's beaches. That's 7.5 billion trillion grains. Every beach you've ever walked on, every coastline, every desert, every grain of sand on the entire planet. 7.5 quintillion grains total for every single grain of sand on every beach on Earth. There are roughly 27 stars in the observable universe. Think about that ratio. Pick up a handful of sand next time you're at the beach. You're holding perhaps a few thousand grains, maybe 10,000 if your hand is large and you really pack it in. For each one of those tiny specks, there are dozens of stars scattered across the cosmos. Each star is a massive ball of nuclear fire, most likely surrounded by planets existing in a galaxy somewhere in the vast expanse of space. And your handful of sand represents just a tiny, tiny fraction of the total. Some popularizations say there are 10 stars per grain of sand. Others say 50. The exact ratio depends on which estimate you use for the total grains of sand on Earth, but the order of magnitude is correct. Somewhere between 10 and 100 stars exist for each grain of beach sand on our planet. Let's try another perspective. Imagine every person currently alive on Earth started counting stars right now. All 7.8 billion of us. Each person counts one star per second without stopping. No sleep, no food, no rest. Just constant counting, 24 hours a day, 7 days a week. How long would it take humanity to count all 200 billion trillion stars? About 800 years. 8 centuries of continuous counting by every person alive. 30 to 40 generations would be born, grow up, grow old, and die during the count. Entire civilizations could rise and fall. Nations that don't exist today would emerge, flourish for centuries, and collapse into history, all while humanity continued counting, and we'd still barely finish. This helps illustrate just how fantastically large this number is. It's not just big, it's beyond the scale of anything humans normally deal with. It exists in a realm of magnitude completely divorced from everyday experience. But here's something crucial to understand. That number 200 billion trillion stars only counts the stars in the observable universe. That's an important distinction. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is approximately 13.8 billion years old. Light travels at 186,000 miles per second, the cosmic speed limit, the fastest anything can move. In 13.8 billion years, you might think light could travel 13.8 billion light years. But the universe has been expanding while that light was traveling through space. Space itself has been stretching, carrying galaxies along with it. By the time light from very distant objects reaches us, those objects have moved much farther away than they were when the light was originally emitted. The fabric of space itself has expanded, increasing the distance. Because of this expansion, the edge of the observable universe is not 13.8 billion light years away. It's approximately 46.5 billion light years in every direction. The observable universe has a diameter of about 93 billion light years. That's roughly 546 sextillion miles. This is our cosmic horizon. Beyond this distance, light hasn't had time to reach us yet, not because those regions don't exist, but because the light is still in transit, or in some cases will never reach us, because space is expanding faster than light can traverse it. Here's the critical question that should make your head hurt. Does the universe end at the edge of the observable universe? Or does it continue beyond that horizon? Most evidence suggests it continues, possibly much farther, perhaps infinitely far. If the universe is infinite, then the number of stars is also infinite, literally infinite. Not just a very large number, but an endless quantity that keeps going forever. There would be infinitely many galaxies, each containing billions or trillions of stars stretching on forever in all directions. In an infinite universe with roughly uniform matter distribution, every possible configuration of matter would occur somewhere. And because there's infinite space, every configuration would occur infinitely many times. There would be infinitely many galaxies identical to the Milky Way, infinitely many planets identical to Earth, down to every grain of sand, every mountain, every ocean. Infinitely many versions of you reading these exact words right now, wondering about the same cosmic questions. This sounds like science fiction, but it's a serious implication of an infinite universe. If space goes on forever and matter is spread out roughly evenly on large scales, then every possible arrangement must eventually repeat simply because there are infinite opportunities for it to occur. We don't know if the universe is actually infinite. We can't see beyond the observable universe, so we can't measure whether space continues indefinitely. Current cosmological models are consistent with either a finite but extremely large universe or an infinite one. The data doesn't yet distinguish between these possibilities. What we can say with confidence is that the observable universe contains approximately 200 billion trillion stars. Everything beyond that is speculation, though educated speculation based on our best understanding of physics and cosmology. Every night, every time you exhale, approximately 3,000 new stars are being born somewhere in the observable universe. 3,000 stellar furnaces igniting for the first time as clouds of gas collapse under their own gravity and reach the critical temperature and pressure for nuclear fusion to begin. 200 billion trillion stars. But what are they? What's actually burning inside those balls of fire? A star is a sphere of plasma held together by its own gravity. Plasma is a state of matter so hot that electrons are stripped away from atoms, creating an ionized gas where nuclei and electrons move independently. This only happens at extreme temperatures, the kind of heat that exists in stellar cores and nowhere naturally on Earth. At the center of a star, if it's massive enough and hot enough, nuclear fusion occurs. Our sun fuses hydrogen into helium in its core. The temperature there reaches about 15 million degrees Celsius. At these temperatures, hydrogen nuclei move fast enough to overcome the electrical repulsion between positively charged protons and fuse together. Every second, the sun converts about 600 million metric tons of hydrogen into helium. In the process, about 4 million metric tons of mass simply disappear, converted directly into energy, following Einstein's famous equation EMC2. That vanished mass becomes the light and heat that makes life on Earth possible. The sun's power output is approximately 380 trillion watts. That's 3.8 x 10^26 watts. Every second, the sun pumps out more energy than human civilization has used in its entire history. And the sun is an average star, nothing special, just one of hundreds of billions like it in our galaxy alone. The photon that hits your face on a sunny afternoon was created in the sun's core tens of thousands of years ago, possibly 100,000 years ago. It was born in a fusion reaction when two hydrogen nuclei merged. But the sun's interior is so dense that photons can't travel in straight lines. They bounce off particles, scatter, get absorbed, and re-emitted, taking a random walk through the dense plasma. It takes millennia for a photon to work its way from the core to the surface. Only then can it stream freely through space, taking just 8 minutes to cross the 93 million miles to Earth. Not all stars are like the sun. They come in a spectacular variety of sizes, temperatures, colors, and lifetimes. We can divide them into 3 broad kingdoms. Red dwarfs are the most common, making up about 70 to 75% of all stars. They're small with masses between 8% and 50% of the sun's mass. They're cool and dim, glowing with a dull red light, but they burn their fuel incredibly slowly. A red dwarf can shine for trillions of years. The universe is only 13.8 billion years old, which means none of the red dwarfs that have ever formed have died yet. Every single red dwarf ever born is still alive today, still steadily fusing hydrogen in their cores. If 3/4 of 200 billion trillion stars are red dwarfs, that's about 150 billion trillion red dwarfs scattered across the cosmos. And here's the remarkable thing, not a single one is visible to the naked eye from Earth, despite being the most numerous stellar type in existence. They're all too faint. The closest red dwarf to Earth, Proxima Centauri, which is only about 4 light years away, requires a telescope to see. The most common citizens of the universe are completely invisible to human eyes. Yellow dwarf stars like our Sun make up about 7 to 8% of all stars. They live for roughly 10 billion years before exhausting their core hydrogen and swelling into red giants. That's still about 14 billion trillion sun-like stars in the observable universe. 14,000 trillion stars, similar to the one that makes life on Earth possible. Then you have the massive stars, blue and white giants and supergiants, some over 100 times the sun's mass. These are rare, perhaps 1% of all stars, or less, but they're spectacularly bright. A single massive blue star can outshine 100,000 suns. These stars live fast and die young, exploding as supernovae after only a few million years. They're cosmic mayflies, brilliant but brief. Let's calculate the total power output of all these stars. 200 billion trillion stars multiplied by an average power output similar to the sun gives about 7.6 to 49 watts. That's 76,000 billion trillion watts flooding through space constantly. It's a number so large, it becomes meaningless. But it represents the total energy output of every star in the observable universe every single second. 75% of all stars are red dwarfs, invisible to the human eye. If your eyes could somehow perceive red dwarfs, the night sky would be transformed. Where you currently see dozens of stars, you'd see thousands. The darkness between constellations would fill in with fainter red points of light until the entire sky glowed with a crowded stellar field. The most populous citizens of the universe are the ones no one can see. Red dwarfs are like the IT staff of the universe. They do 75% of the work, keeping the cosmos running, but nobody notices them because they don't make any noise. When we count 200 billion trillion stars, we are not just counting active living stars. We're counting stellar corpses too. White dwarfs, the cooling remnants of stars like the sun, number in the tens of billions of trillions. Neutron stars, the crushed cores left by supernova explosions, number in the hundreds of billions. Black holes regions, where gravity has become so strong that not even light can escape, number in the billions across the observable universe. These objects aren't actively fusing elements anymore. Their nuclear fires have gone out, but they're still there, still part of the senses. White dwarfs will cool for trillions of years, slowly fading from the white-hot to red, to eventually becoming black dwarfs, cold spheres of carbon and oxygen floating through space. Neutron stars spin rapidly, some pulsing hundreds of times per second. Like cosmic lighthouses, black holes lurk invisibly, revealing themselves only through their gravitational effects on nearby matter. The photon that struck your eye from the sun this morning, it was created in the solar core roughly 100,000 years ago, when Neanderthals still walked through Ice Age Europe, when modern humans were just beginning to spread out of Africa. That ancient photon bounced around inside the sun for 100 millennia before finally escaping and making the 8-minute journey to Earth, where it entered your eye and allowed you to see 200 billion trillion nuclear reactors. Most of them have planets orbiting around them. How many worlds are out there? And are they alone? Let's talk about planets, because stars rarely exist alone. And the numbers we're about to discuss will make 200 billion trillion stars seem like just the beginning. For most of human history, we knew of only one planetary system, ours. We had the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto before astronomers demoted it. 9 planets, then 8. That was it. That was the entire catalog of known worlds. We suspected other stars had planets. It made sense. If our sun had a family of worlds orbiting it, why wouldn't other stars? But suspecting and knowing are different things. We had no way to detect planets around distant stars. They were too small, too dim, too close to their parent stars to see directly. Then, 1995 changed everything. Astronomers found the first confirmed planet orbiting a sun-like star. It was a gas giant, about half Jupiter's mass, but it was orbiting incredibly close to its star, completing a full orbit in just over 4 days. This was nothing like our solar system. It was exotic, strange, unexpected. Since that discovery, the floodgates opened. Between 1995 and 2025, we've confirmed over 6,000 planets orbiting stars other than our sun. Thousands more candidates await verification. The Kepler Space Telescope, operating from 2009 to 2018, revolutionized the field. It stared at a single patch of sky containing about 150,000 stars and watched for tiny dips in brightness when planets passed in front of their stars. The data revealed something remarkable. Planets aren't rare, cosmic accidents. They're common, very common. Most stars have at least one planet. Many have multiple planets. Some have 7, 8, or more worlds in complex orbital dances around their parent star. Planetary systems appear to be the default outcome of star formation, not a special case, not a lucky coincidence. When a star forms from a collapsing gas cloud, leftover material naturally settles into a rotating disk. Dust particles in that disk collide and stick together, growing larger. Pebbles become boulders. Boulders become mountains. Mountains become planet-sized objects. The process takes about 10 million years for rocky planets, possibly longer for gas giants. This happens across the universe constantly. If most of 200 billion trillion stars have planets, and most stars have multiple planets, we're talking about at least 300 billion trillion planets scattered across the observable universe. Think about that number. 300 billion trillion worlds. That's 3 followed by 23 zeros. 300,000 planets. If you counted one planet per second without stopping, It would take you 9.5 million years just to count them all. You'd need to have started counting when humans and chimpanzees shared a common ancestor. But we're particularly interested in a specific type of planet: rocky worlds in habitable zones, the regions around stars where temperatures allow liquid water to exist on a planet's surface. Water, as far as we know, is essential for life. Too close to the star, and water boils away. Too far, and it freezes solid. But in that Goldilocks zone, not too hot, not too cold, liquid water can flow. Based on Kepler data, roughly 20 to 50% of Sun-like stars have at least one rocky planet in the habitable zone. Let's be conservative and say 20%. 20% of 14 billion trillion Sun-like stars is about 3 billion trillion potentially habitable planets. 3 billion trillion worlds where conditions might be right for life. That's 3,000 Earth-like planets. 3 million billion worlds with the right temperature, the right distance from their star, possibly the right atmosphere. Now here's where speculation gets interesting. We have no idea how common life actually is. Our sample size is exactly one Earth. We don't know if life arises easily given the right conditions, or if it's incredibly rare, requiring a series of unlikely accidents that almost never happen. But let's play with the numbers. If only 1 in a million habitable planets actually develops life, that's still 3 quadrillion living worlds. 3,000 trillion planets where something grows, reproduces, evolves. Bacteria in underground oceans, algae in shallow seas, forests under alien skies. If only 1 in a billion of those living worlds develops intelligent life, capable of building civilizations, that's still 3 trillion technological societies, 3 million civilizations scattered across the cosmos. Some might be far ahead of us, having existed for millions of years. Others might be behind, still learning to control fire or invent the wheel. Every night, there could be 3 trillion civilizations looking up at their own skies, wondering the same question. We're wondering, are we alone? And here's the puzzle. We've found no evidence of other life, no radio signals carrying messages across the void, no massive engineering projects visible across interstellar distances, no signs that anyone else is out there. The universe, for all its vastness, appears silent. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If there are billions or trillions of potential homes for life, and the universe has had 13.8 billion years for life to arise and evolve and spread, we should see evidence. But we don't. Maybe life is extraordinarily rare, and we're alone, or nearly alone. Maybe intelligence is the difficult step. Maybe civilizations inevitably destroy themselves before spreading to the stars. Maybe they're hiding, staying quiet for reasons we don't understand. Maybe the distances between stars are simply too vast for contact to be practical. The universe is like a massive party with millions of rooms, but everyone's staying in their own space, never meeting each other. Or perhaps the party already happened, and we arrived late after everyone else left. Or we're the first ones here early to a gathering that won't really get started for another billion years. We don't have answers. What we do have is opportunity. With 300 billion trillion planets, the sheer number of chances for life to arise is staggering. Even extremely low probabilities become near certainties when multiplied by such enormous numbers. But before we search for them out there among those countless worlds, let's turn the question inward. Let's ask about you, about where you came from. Not your parents or grandparents, but deeper. Where did the atoms that make up your body come from? How did you, a conscious being, capable of asking these questions, come to exist on this particular planet orbiting this particular star? The answer connects you directly to those 200 billion trillion stars in a way that's profound and beautiful. You're not separate from the cosmic story we've been telling. You're part of it, made by it. You are quite literally the universe looking back at itself. And that story begins not with planets or stars, but with the Big Bang itself and the first 3 minutes of cosmic history. This isn't a metaphor. It's not poetic language meant to make you feel connected to the cosmos. It's chemical fact. You are made of stardust, and I can prove it. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur everywhere, not just inside stars. The temperature was about 10 billion degrees. In those first 3 minutes, the universe created hydrogen, helium, and tiny amounts of lithium. That's it. 3 elements total. The entire periodic table you learned in school, all 118 elements, was reduced to just 3. Hydrogen, the simplest atom, made up about 75% of all matter. Helium accounted for about 25%. Lithium was barely a trace. Everything else, every other element in the universe, was created later inside stars. Carbon, the foundation of all life we know. Nitrogen, essential for DNA. Oxygen, which you're breathing right now. Iron, flowing through your blood. Calcium, giving structure to your bones. Gold, platinum, uranium. None of these existed in the early universe. Stars are element factories. They take simple hydrogen and helium, and through nuclear fusion in their cores, forge progressively heavier elements. The process works like this. In the core of a star, hydrogen nuclei are squeezed together at enormous temperatures and pressures. They overcome their natural repulsion and fuse into helium, releasing energy. When the hydrogen runs out, the core contracts and heats up even more. If the star is massive enough, it gets hot enough to fuse helium into carbon and oxygen. More massive stars continue the process, fusing carbon into neon and magnesium, then oxygen into silicon and sulfur, then silicon into iron. Iron is where the process stops in normal stellar fusion. Fusing iron doesn't release energy, it consumes energy, so stars can't burn iron as fuel. But the heaviest elements, the gold and platinum and uranium, require even more extreme conditions. They're created in supernova explosions, when massive stars die in spectacular violence. The explosion releases so much energy that elements heavier than iron can be synthesized in the blast. When a massive star explodes, it scatters all these newly created elements into space at thousands of miles per second. That enriched material, containing carbon and oxygen and iron and gold, mixes with existing gas clouds floating through the galaxy. Eventually, those gas clouds collapse to form new stars and planets. The new stars and planets are made from material that includes the ashes of previous stellar generations. This cycle has been operating for over 13 billion years. The first stars, called Population 3, stars formed about 100 to 200 million years after the Big Bang. They contained almost pure hydrogen and helium, no heavy elements at all, because no previous stars had died to create them. These first stars were probably massive, perhaps 100 to 1,000 times the Sun's mass. They lived fast, maybe only a few million years and exploded as supernovae. Those explosions created and scattered the first heavy elements into the universe. The next generation of stars, population 2 stars, formed from gas that was slightly enriched, maybe 0.01% heavy elements. Not much, but enough to be different from the first generation. Our sun is probably a third or fourth generation star, formed about 4.6 billion years ago. The gas cloud it formed from contained about 2% heavy elements by mass. That small percentage, just 2%, made all the difference. Those elements allowed rocky planets like Earth to form and provided the building blocks for life. Here's the connection to you. Every atom in your body, except for hydrogen, was created inside a star. The oxygen you're breathing was forged in stellar cores billions of years ago, probably, in a massive star that exploded as a supernova 7 or 8 billion years ago, before our solar system even existed. The calcium in your bones came from dying stars. When massive stars reach the end of their lives, they create calcium through fusion in their cores. Then, they explode, scattering that calcium into space. The iron in your blood, essential for carrying oxygen through your body, was synthesized in supernova explosions. Every atom of iron on Earth was created in the violent death of a massive star. This isn't metaphorical. You aren't like stardust. You are stardust, recycled through multiple stellar generations. The atoms that compose you were created through nuclear fusion in stellar interiors, over billions of years scattered into space. When those stars died, incorporated into a gas cloud that eventually collapsed to form the sun, and planets accreted onto Earth, and ultimately became part of living organisms. You're the product of cosmic alchemy, elements born in stars, forged in explosions, drifting through space, eventually finding their way into the molecules that make up your cells. Every breath you take contains oxygen atoms from ancient supernovae. Every thought you think is enabled by calcium ions from stellar cores that burned out billions of years ago. With 200 billion trillion stars operating as element factories over billions of years, the universe has produced staggering quantities of heavy elements. There's enough carbon scattered through the cosmos for countless rocky worlds, enough oxygen for atmospheres and oceans on billions of planets, enough silicon and iron for planetary crusts and cores across the observable universe. The number of stars directly translates to the total chemical enrichment of the universe. More stars means more fusion, more element production, more raw material for complex chemistry, and potentially more raw material for life. You're not just connected to the stars, you're made of them. The universe spent 13 billion years preparing the ingredients that eventually became you. Multiple generations of stars lived and died so that the atoms in your body could exist. That's not poetry. That's the scientific reality of your cosmic ancestry. You don't just live in the universe, you're made from it. And that brings us to the next question. How are all those 200 billion trillion stars arranged in space? What does the large-scale structure of the universe actually look like? Stars don't scatter randomly through space like grains of salt spilled on a table. They organize into structures at multiple scales, creating a pattern that looks nothing like you'd expect. Let's build up the hierarchy. Stars cluster into galaxies. We've established that. The Milky Way contains about 200 billion stars, organized into a rotating disk with spiral arms. Galaxies in turn cluster into groups and clusters. Our Milky Way belongs to the local group, a collection of about 54 galaxies. Besides the Milky Way and Andromeda, the two dominant members, the rest are mostly dwarf galaxies containing a few billion stars each. The entire local group spans about 10 million light years, or roughly 59 trillion miles. The local group is part of something larger, the Laniakea supercluster. This massive structure contains about 100,000 galaxies spread across 520 million light years, or roughly 3 quadrillion miles. The name Laniakea means immeasurable heaven in Hawaiian, which is fitting given its scale. Laniakea isn't held together by gravity alone like a galaxy or cluster. It's more of a region defined by galaxies' motions toward a common gravitational center called the Great Attractor, a concentration of mass pulling galaxies toward it like water flowing toward a drain. But even superclusters aren't the end of the hierarchy. When you map the entire observable universe, you see something extraordinary: the cosmic web. Galaxies concentrate in thin filaments, forming interconnected strands with enormous voids between them. The structure resembles soap foam. Galaxies gather in thin sheets and filaments like soap film, while the voids are like air bubbles, mostly empty. The largest known structure is the Hercules corona borealis, Great Wall, a filament of galaxies about 10 billion light years long, or roughly 59 octillion miles. It's so large, it challenges our understanding of how structures form in the universe. This cosmic web arose from tiny density fluctuations in the very early universe, less than a second after the Big Bang. Quantum fluctuations created regions that were slightly denser than average, maybe 1 part in 100,000 denser than their surroundings. Those slightly denser regions had slightly more gravity, so they attracted more matter, becoming denser still. Over hundreds of millions of years, this process amplified. Dense regions became filaments and clusters. Less dense regions lost matter to their denser neighbors, becoming voids. Gravity shaped the raw material of the universe into the web we see today. It's a structure that grew organically over billions of years, driven by gravity acting on the initial conditions set down in the first fraction of a second after the Big Bang. Here's what this means for the distribution of those 200 billion trillion stars. They're not evenly spread through space. Most exist along these filaments and in clusters where the filaments intersect. The voids between filaments contain relatively few galaxies. If you picked a truly random point in space, you'd probably land in a void far from any galaxy. The distances to the nearest stars would be measured not in light years, but in millions of light years. You'd be surrounded by emptiness in every direction, with the faint smudges of distant galaxies providing the only evidence that anything else existed in the universe. Stars, for all their vast numbers, occupy only a tiny fraction of the total volume of space. The universe is mostly empty. If you calculated the volume occupied by stars themselves, not the space between them, but the actual stellar material, it would represent less than 0.0, or 1% of the total volume of the observable universe. The universe is like a pizza, where the toppings, the stars and galaxies, make up less than 1% of the total, and the rest is just dough, empty space stretching endlessly in all directions. The distances between stars within galaxies are already enormous. The nearest star to our Sun is Proxima Centauri, about 4.2 light years away, or roughly 25 trillion miles. If you randomly appeared somewhere in the Milky Way, you'd most likely be in interstellar space, with the nearest star years away, even traveling at light speed. If you randomly appeared somewhere in the universe, you'd almost certainly die in darkness before ever seeing starlight. The void would claim you instantly, the cold and vacuum ending your existence before your eyes could adjust to see the distant, faint glow of faraway galaxies. This structure, this cosmic web of filaments and voids, isn't static. It's changing. Gravity continues pulling matter together. Filaments continue growing. Clusters continue merging. The large-scale structure of the universe is still evolving, still being shaped by the same forces that created it billions of years ago. And that brings us to a crucial question we need to address. What happens next? If the structure is still changing, if galaxies are still moving, still colliding, still merging, what does the future hold for those 200 billion trillion stars? Most stars don't exist in isolation like our Sun. The majority live in binary or multiple star systems where two or more stars orbit each other gravitationally bound for billions of years. In a binary system, two stars orbit their common center of mass, performing a gravitational dance that can last for the entire lifetime of both stars. These systems are incredibly common. Roughly half of all Sun-like stars exist in binary or multiple star systems. For more massive stars, the fraction is even higher, perhaps 70 to 80%. Think about what this means for our senses. If half of 200 billion trillion stars are in binary systems, we're talking about 100 billion trillion binary pairs. That's 100,000, 1,000,000,000,000,000,000 stellar couples waltzing through space, locked in eternal orbits around each other. Some binaries are wide, with the two stars separated by hundreds of astronomical units, about 100 to 200 times Earth's distance from the Sun. These stars orbit each other over thousands of years and barely influence each other's evolution. They're like distant neighbors who wave occasionally but otherwise live separate lives. Other binaries are close with stars separated by only a few times their own diameters. These systems are fascinating because the stars can exchange material. If one star swells into a red giant, its outer atmosphere might spill over onto its companion, like water overflowing from one cup into another, sitting right beside it. This mass transfer can dramatically affect both stars' evolution. The star receiving material can spin up, rotating faster and faster as angular momentum transfers along with the gas. The star losing material can be stripped down to its core, becoming something completely different than it would have been alone. Some close binaries are so tight that the stars actually touch, sharing a common envelope of gas. These contact binaries look like peanuts, two stars merged together, but each maintaining its own core. They're among the strangest objects in the sky. Binary star systems produce some of the most spectacular events in astronomy. Type Aya supernovae, which we use as distance indicators to measure the universe, occur in binary systems where a white dwarf accumulates material from its companion until reaching critical mass and exploding. The white dwarf sits there, pulling gas from its companion star. The gas spirals onto the white dwarf's surface, building up over thousands or millions of years. When the white dwarf's mass reaches about 1.4 times the sun's mass a threshold called the Chandrasekhar limit. It can no longer support itself. The entire star detonates in a thermonuclear explosion so violent it briefly outshines an entire galaxy. Nova outbursts happen when a white dwarf in a binary system accretes hydrogen from its companion. The hydrogen builds up on the white dwarf's surface until conditions are right for explosive fusion. The white dwarf briefly brightens by thousands of times, appearing as a new star in the sky, hence nova, meaning new. Then it fades back to normal, only to repeat the cycle years or decades later. But let's talk about what happens when stars die and leave behind remnants far stranger than white dwarfs. When a massive star, say 10 to 20 times the sun's mass, exhausts its fuel, the core collapses catastrophically. The collapse happens in less than a second. The core, roughly the size of Earth, shrinks to about 12 miles or 20 kilometers across. Electrons and protons are crushed together, forming neutrons. The result is a neutron star, an object so dense that a teaspoon of neutron star material would weigh about 900 billion kilograms on Earth. That's about 150 times the mass of the Great Pyramid of Giza in a single teaspoon. The surface gravity is about 100 billion times Earth's gravity. If you could somehow stand on a neutron star's surface, you'd weigh the same as a small mountain does on Earth. Your body would be crushed instantly into a layer of atoms, just a few atoms thick, spread across the star's surface. Many neutron stars are pulsars, spinning rapidly and beaming radiation from their magnetic poles like cosmic lighthouses. As the star rotates, the beam sweeps past Earth, and we detect a pulse. Some pulsars spin hundreds of times per second, rotating faster than a kitchen blender on high speed. The fastest known pulsar spins over 700 times per second. It completes a full rotation in less than 2 milliseconds. The surface of this star is moving at about 20% the speed of light. Matter at the equator is held down only by the neutron star's immense gravity. Any faster, and the star would tear itself apart. These millisecond pulsars are the most precise clocks in nature. Their rotation is so stable that astronomers use them to detect gravitational waves, ripples in space-time itself, passing through the galaxy. Then there are magnetars, neutron stars, with ultra-strong magnetic fields, 1,000 trillion times Earth's magnetic field. These fields are so intense, they can distort atoms, stretching them into cigar shapes. The fields can trigger violent outbursts, suddenly releasing enormous amounts of energy in bursts of X-rays and gamma rays. In December 2004, a magnetar flare occurred about 50,000 light-years away, roughly 294 quadrillion miles from Earth. The burst of radiation was so intense, it temporarily blinded every X-ray satellite in orbit, despite originating halfway across the galaxy. If that magnetar had been just 10 light-years away, instead of 50,000 hours, the radiation would have triggered a mass extinction on Earth. And beyond neutron stars lie black holes, objects where gravity has become so strong that not even light can escape. When the most massive stars die stars over about 20 times the sun's mass, their cores collapse beyond the neutron star stage into black holes. The collapse creates a region of space where space-time itself is so severely warped that nothing, not matter, not light, not information of any kind, can escape once it crosses the event horizon. The core shrinks to a point of infinite density, called a singularity, though what actually happens at the singularity remains one of the deepest mysteries in physics. Black holes range in size from a few times the sun's mass to billions of times the sun's mass. The supermassive black holes at the centers of galaxies contain millions or billions of solar masses compressed into regions smaller than our solar system. Now here's what this means for our census of 200 billion trillion stars. That number includes living stars currently fusing hydrogen or helium in their cores. But it also includes stellar remnants, the corpses of stars that died long ago. There are tens of billions of trillions of white dwarfs scattered through the universe, the cooling remnants of stars like the sun. There are hundreds of billions of neutron stars, the crushed cores left by supernova explosions. There are billions of black holes, collapsed stars, where gravity has won its final victory over all other forces. When we count stars, we're counting the full life cycle. Stars being born in collapsing gas clouds, middle-aged stars steadily fusing elements, dying giants shedding their outer layers, stellar remnants cooling slowly over trillions of years. Every second, millions of stars are dying somewhere in the observable universe. Millions more are being born to replace them. The universe is like a massive living organism, constantly recycling material, constantly creating and destroying a cosmic metabolism operating on timescales of millions and billions of years. The stellar population isn't static, it's dynamic, evolving, changing. Stars live and die. Their deaths seed the next generation. The process has been running for 13.8 billion years and will continue for trillions more. But here's something crucial to understand. This cycle won't last forever. The peak of star formation already passed billions of years ago. The universe is making fewer new stars now than it used to. The golden age of star formation is behind us. The countdown has already begun. Galaxies don't exist in isolation. They interact, collide, and merge, dramatically reshaping their stellar populations over billions of years. When two galaxies collide, something counterintuitive happens. The stars themselves rarely hit each other. The distances between stars are so vast compared to their sizes that two galaxies can completely interpenetrate without a single stellar collision. Space is mostly empty, remember, but the gas clouds do collide. When giant molecular clouds from two galaxies slam together at hundreds of miles per second, the collision compresses the gas, triggering intense bursts of star formation. The shock waves rippling through the gas cause it to collapse, fragmenting into thousands of dense clumps that become new stars. The antenna galaxies, about 70 million light years away, or roughly 412 quadrillion miles from Earth, are a spectacular example of this process in action. Two spiral galaxies are currently in the process of merging. Long tidal tails of stars and gas stream away from the collision site, created by gravitational interactions between the two galaxies, pulling stars into long tendrils. Within the collision zone, thousands of young star clusters are forming, each containing tens of thousands of newly born stars. The two galaxies are blazing with new stellar birth, triggered by the collision. In about 1 billion years, the merger will complete, forming a single large elliptical galaxy. The spiral structure will be destroyed. Most of the gas will be consumed in star formation or blown away by supernova winds and stellar radiation. The resulting elliptical will be a graveyard of old stars with little ongoing star formation, a monument to the violence that created it. This process is common throughout the universe. Most large elliptical galaxies probably formed from mergers of smaller spirals. When you look at a giant elliptical galaxy containing 1 trillion stars, you're looking at the product of multiple mergers over billions of years. Our own Milky Way has absorbed several small dwarf galaxies over its lifetime. Evidence appears in stellar streams, rivers of stars from destroyed dwarf galaxies now orbiting through the Milky Way's halo. These streams are like fossil evidence of ancient collisions, the remnants of galaxies that no longer exist as independent objects, and we're heading for a major collision ourselves. Andromeda and the Milky Way are approaching each other at about 110 kilometers per second, or roughly 68 miles per second. The distance between us is shrinking by about 2,000 miles every second. In about 4 billion years, they'll collide. The merger will be a slow-motion catastrophe playing out over hundreds of millions of years. First contact will probably happen in about 3.85 billion years, when the outer regions of the two galaxies begin to interact. The collision will trigger massive star formation as gas clouds collide. The night sky for any observers on Earth, if Earth still exists, will be spectacular. New massive stars will light up in brilliant blue clusters scattered across the sky. The cores of both galaxies will be visible simultaneously, two bright bulges moving closer together over millions of years. Our sun will likely survive the collision. It'll be thrown into a different orbit, possibly ending up farther from the merged galaxy's center, possibly closer. The solar system as a whole will probably emerge intact. The distances between stars are so vast that the chance of another star passing close enough to disrupt planetary orbits is tiny, though not zero. But the night sky will change dramatically. 3 billion years from now, as the galaxies approach Andromeda, will grow larger in Earth's sky, eventually spanning several degrees, 10 or 20 times the width of the full moon. It will dominate the night, a vast spiral stretching across the heavens, growing larger year by year. When the galaxies interpenetrate for observers on Earth, it will look like living inside a cosmic fireworks display. New stars will blaze into life. The galactic nuclei will pass close to each other, or even merge, creating a brief period of intense activity as both supermassive black holes interact. Eventually, after several close passes and perhaps 1 billion years of interaction, the two galaxies will settle into a single, massive elliptical galaxy. Astronomers have already given it a name, Milkomeda. Galaxy mergers look dramatic, but in a way they're like two clouds passing through each other. The individual particles, the stars, don't collide. They just get their orbits scrambled, thrown into new paths by the gravitational chaos. It looks violent from a distance, but for the stars themselves, it's a relatively gentle process. This is happening across the universe constantly. Thousands of galaxy collisions and mergers are occurring right now in the observable universe. At any given moment, thousands of galaxies are in various stages of merger, from first contact to final coalescence. In the early universe, galaxies were smaller and closer together. Collisions and mergers were common. Large galaxies grew by cannibalizing smaller ones. This hierarchical assembly built the diverse galaxy population we see today. Even now, interactions continue. The Milky Way is slowly tearing apart the Sagittarius dwarf elliptical galaxy, one of our satellite galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere as faint smudges in the sky, are slowly being disrupted by tidal forces from the Milky Way. In several billion years, they'll likely merge with us completely. With 2 trillion galaxies in the observable universe, and many of them interacting or merging, the total stellar population is being constantly reshuffled. Stars that formed in one galaxy end up in another. Stellar populations mix and blend. The boundaries between galaxies become fluid. Your descendants, if any exist in 4 billion years, might witness the collision of 2 galaxies, a cosmic spectacle playing out over millions of years in the sky above them. They'll watch as the Milky Way and Andromeda become one. And this brings us to a critical question about the future. We've talked about how stars are born, how they live, how they die. We've discussed binary systems and stellar remnants. We've seen galaxies collide and merge. But all of this, the entire cosmic story we've been telling, is about the present and the recent past. What about the far future? The number of stars right now is 200 billion trillion. But what about a billion years from now? A trillion years from now? The story isn't finished. The universe is still evolving. And to understand where it's going, we need to talk about stellar life cycles on cosmic timescales and the ultimate fate of star formation itself. That's what we'll explore in the final episode. The universe is dying. Not quickly, not dramatically, but the decline has already begun, and most people don't realize it. Star formation in the universe peaked about 10 to 11 billion years ago, when the universe was roughly 3 billion years old. Back then, galaxies were smaller, denser, and gas-rich. Stars formed at a furious pace, perhaps 10 times the current rate. The universe blazed with young hot stars, lighting up every corner of space. That was the golden age of the cosmos, the peak, the zenith of stellar birth. Since then, star formation has been declining. The rate has dropped steadily over billions of years. Much of the available gas has been consumed, fused into stars that now shine across the universe. What remains is less efficient at forming stars, either too dispersed or too hot, or locked away in galaxies that have exhausted their reserves. Currently, the Milky Way forms about 3 to 5 new stars per year. That might seem like a lot. 3 to 5 new nuclear furnaces igniting every year in our galaxy alone. Multiply across 2 trillion galaxies, and you get trillions of new stars being born annually across the observable universe. But it's nothing compared to the past. 10 billion years ago, the Milky Way was probably forming dozens of stars per year, maybe more. The night sky would have been brighter, more crowded with young blue stars that burned fierce and hot. We live in the twilight era of the universe. The golden age passed billions of years ago. We arrived late to the party after the peak of the celebration, when things are winding down, but still spectacular enough to be worth experiencing. Why is star formation declining? The answer is simple. We're running out of fuel. Stars form from hydrogen gas in giant molecular clouds. But hydrogen gas doesn't last forever. It gets consumed, locked into stars, where it fuses into helium, blown out of galaxies by supernova explosions and stellar winds, heated to temperatures too high for gravity to pull it together into new stars. Every generation of stars consumes some of the available gas. Some gets recycled, when stars die blown back into space to form new stars, but some is locked away permanently in white dwarfs and neutron stars and black holes, removed from the cycle forever. Over time, the total amount of gas available for star formation decreases. The universe is slowly converting its hydrogen into stars and stellar remnants, like a bank account being drawn down with each generation. Eventually, star formation will slow further and then cease entirely. The last stars will form perhaps 1,000,000,000,000 years from now, give or take. After that, no new stars will be born. Galaxies will have exhausted their gas reserves completely. Existing stars will continue shining for a while. The sun has about 5 billion years left before it exhausts its hydrogen fuel. Stars like the sun will last 10 billion years total. Larger stars burn faster, living only millions of years. Smaller stars burn slower. Red dwarfs the smallest stars. The ones that make up 70 to 75% of all stars will last the longest. A red dwarf can shine for 1,000,000,000,000 years, or more, slowly fusing its hydrogen at a pace so leisurely it would take longer than the current age of the universe to exhaust its fuel. In fact, none of the red dwarfs that have ever formed have died yet. Not a single one. The universe isn't old enough. Every red dwarf born in the first billion years after the Big Bang is still shining today, still fusing hydrogen, still pumping out energy at a steady, patient pace. These red dwarfs will be the last lights in the universe. In about 100 trillion years, most stars will have burned out. The blue giants and yellow dwarfs will have died long ago, exploding as supernovae or fading as white dwarfs. Only the red dwarfs will remain scattered through the darkness, keeping vigil. In the far future, measured in timescales that make the current age of the universe look like an eye blink, those last red dwarfs will exhaust their fuel and fade. The universe will go dark. No more stars. No more fusion. Just stellar remnants, cooling slowly in an expanding void. White dwarfs will fade to black dwarfs, cold cinders of carbon and oxygen that no longer emit light. Neutron stars will cool their surfaces, dropping to near absolute zero. Black holes will sit in the darkness, patient and eternal, slowly evaporating through Hawking radiation over timescales of 10 to the 100th power years. The universe of the far future will be cold, dark, and empty, a graveyard of dead stars expanding forever into the void. But that's so distant, it's almost meaningless to contemplate. For now and for billions of years to come, stars will continue lighting up the cosmos. The number we count today, 200 billion trillion stars, will remain roughly stable. The birth rate and death rate are still balanced enough that the total population doesn't change dramatically. You're lucky. You were born at exactly the right time to see the universe in its glory. Not during the golden age when star formation peaked, but during an era when the universe is still magnificent, still filled with light, still actively creating new stars. Even as the overall rate declines, you're living in an epoch when the cosmos is mature, but not yet old, still vibrant, but past its youth. The night sky is still filled with stars. Galaxies still glow with stellar light. The universe is still bright enough, still active enough to inspire wonder. In 100 trillion years, any conscious beings that still exist, if such beings are even possible, in a dark, cold universe, will look back on our era as the golden age they missed. They'll study the ancient past when stars filled the sky, when galaxies blazed with light, when fusion powered the universe. We're here during that time, right now, this moment in cosmic history when 200 billion trillion stars shine across the observable universe. But the most miraculous thing isn't the number of stars, it's that we measured them. It's that we figured it out. From one small planet, we counted the stars across billions of light years and arrived at a number. That achievement, that capability, is what we need to talk about next. Counting stars across the universe sounds impossible. How do you measure distances to galaxies billions of light years away? How do you count objects so distant their light has been traveling since before Earth existed? The answer is the cosmic distance ladder, one of the most ingenious constructions in all of science. It's a series of overlapping measurement techniques, each building on the previous one, allowing us to measure distances from nearby stars to the edge of the observable universe. The first rung is direct measurement using parallax. As Earth orbits the Sun nearby, stars appear to shift position slightly relative to more distant background stars. The closer the star, the bigger the shift. Measure that shift, and you can calculate distance using simple geometry, the same technique surveyors use to measure distances on Earth. Parallax works well for stars up to a few thousand light years away. The Gaia space mission has measured parallax distances for about 2 billion stars in the Milky Way, with extraordinary precision, accurate to within a few percent for most stars. But beyond a few thousand light years, the shifts become too small to measure accurately, even with Gaia's precision. The angles become so tiny, they're lost in measurement noise. We need something else. The second rung uses a standard candle's objects whose intrinsic brightness is known. If you know how bright something really is, and you measure how bright it appears from Earth, you can calculate how far away it must be. The object appears dimmer the farther away it is following an inverse square law. Cepheid variable. Stars are the most famous standard candles. These pulsating stars brighten and dim in regular cycles, ranging from days to months. Henrietta Leavitt discovered in 1912 that there's a direct relationship between a Cepheid's pulsation period and its intrinsic brightness. Longer period means brighter star. Measure the period, and you know how bright it really is. Compare that to how bright it appears, and you calculate distance. This is exactly what Edwin Hubble used in 1923 to prove Andromeda was a separate galaxy. The Hubble Space Telescope has found Cepheids in galaxies up to about 100 million light years away. Beyond that, even the brightest Cepheids become too faint to detect individually. The third rung uses type Ia supernovae, exploding white dwarfs that reach a critical mass before detonating. Because all type Ia supernovae involve white dwarfs reaching essentially the same mass before exploding, they all have similar intrinsic brightness. They're incredibly luminous, briefly outshining entire galaxies, so they can be seen across billions of light years. By calibrating type Ia supernovae against Cepheid distances in nearby galaxies, astronomers established that type Ia supernovae work as distance indicators. They've been used to measure distances to galaxies billions of light years away, helping establish the universe's expansion rate and revealing the existence of dark energy. For the most distant galaxies approaching the edge of the observable universe, astronomers use redshift. As the universe expands, light from distant objects gets stretched to longer wavelengths shifted toward the red end of the spectrum. The more distant the galaxy, the faster it's receding due to cosmic expansion, and the greater the redshift. By measuring a galaxy's redshift and using models of cosmic expansion, astronomers can estimate its distance. This works for galaxies so distant that no individual stars or supernovae can be resolved galaxies we're seeing as they were billions of years ago. Each rung of the distance ladder has uncertainties. Parallax measurements have small errors, maybe 1 or 2% for nearby stars. Cepheid calibrations aren't perfect, with uncertainties around 5 to 10%. Type Ia supernovae show some variation in brightness that must be accounted for, adding another 5 to 10% uncertainty. Redshift distances depend on models of cosmic expansion that have their own assumptions and uncertainties. By the time you reach the most distant galaxies, the total uncertainty in distance measurements is probably around 10 to 20%. Not perfect, but good enough. The Gaia mission has dramatically improved the foundation of the distance ladder by providing precise parallax measurements for 2 billion stars. The James Webb Space Telescope, operational since 2022, is finding faint galaxies that previous surveys missed, refining our count of how many galaxies exist. When we say the observable universe contains 200 billion trillion stars, that number is accurate to within a factor of 2 or 3. Maybe it's 100 billion trillion. Maybe it's 300 billion trillion. But the order of magnitude is solid. We're not off by factors of 10 or 100. Measuring the universe is like measuring the height of a building with a 12-inch ruler. You can't do it directly. You need multiple steps building on each measurement to reach the next. You measure the first floor, then use that to measure the second, then the third, working your way up. Each step introduces small errors that compound as you go higher. But by carefully cross-checking each method against the others and quantifying uncertainties, you eventually arrive at an answer that's reliable enough to trust. This is how we measured cosmic distances. This is how we counted galaxies across billions of light years. This is how we arrived at 200 billion trillion stars. We figured it out. We built the tools, developed the techniques, made the measurements, and calculated the distances. From one small planet, we measured the universe. But why? Why did we bother? Why spend centuries developing these techniques, building these instruments, making these measurements? What drives humans to count stars? They can never visit to measure galaxies. They can never reach. Your ancestors could see about 20 to 30 miles to the horizon. That was the extent of their directly observable world. For hundreds of thousands of years, humans lived in that limited bubble, knowing only what their eyes could see. A few centuries later, we're counting 200 billion trillion stars. Think about that leap. From, I can see maybe 50 people in my tribe, to, I can count 200,000, 1,000 stars across the observable universe. From estimating dozens to measuring numbers with 23 zeros. We made that jump in roughly 400 years. From Galileo's first telescope in 1609 to the James Webb Space Telescope in 2022. 4 centuries. That's about 16 generations. Your great grandparents lived in a world where the extent of the universe was unknown. You live in a world where we've measured it. This wasn't easy. It required thousands of scientists working over hundreds of years. It required countless wrong turns, failed experiments, revised theories, and refined measurements. It required inventing entirely new technologies just to gather the data needed to make the calculations. We had to invent telescopes capable of seeing across billions of light years. We had to develop photography to capture faint light the eye couldn't see. We had to invent spectrographs to analyze starlight and determine chemical compositions, temperatures, velocities. We had to discover the relationships between stellar properties, like mass, luminosity, and temperature. We had to work out stellar evolution theory to understand how stars change over time. We had to realize that fuzzy nebulae were actually distant galaxies containing billions of stars. We had to develop distance measurement techniques spanning from parallax for nearby stars to redshift for the most distant galaxies. We had to understand cosmic expansion, the Big Bang, and the evolution of structure in the universe. We had to account for dark matter and dark energy, mysterious substances we still don't fully understand, but whose effects we can measure. We had to build satellites and space telescopes to observe in wavelengths blocked by Earth's atmosphere. We had to develop sophisticated image processing and statistical techniques to count galaxies in deep fields and extrapolate to the entire sky. Each step required overcoming enormous technical challenges. Each step required developing new technologies that didn't exist. Each step required people dedicating their careers, sometimes their entire lives, to solving one small piece of the puzzle. And we did it. Humanity collectively, over generations, figured it out. The number we quote today, 200 billion trillion stars, isn't a wild guess. It's not speculation or philosophy. It's a measurement-based estimate with quantified uncertainties. We observed galaxies with telescopes. We counted them in deep survey fields. We measured their distances using the cosmic distance ladder. We estimated their stellar populations based on their light output and color. We extrapolated to the entire observable universe, accounting for observational biases. The result is a number we can actually defend with data and analysis. We might be off by a factor of 2. Maybe it's really 100 billion trillion or 300 billion trillion. But we're not off by factors of 10 or 100. The order of magnitude is correct. You're living in the first era of human history, when we know how small we are. Previous generations could imagine we were important, that Earth was the center of everything, that the universe revolved around us. You don't have that luxury. You know the truth. One planet among 300 billion trillion, one star among 200 billion trillion, one galaxy among 2 trillion, one tiny speck in an incomprehensibly vast cosmos. But here's the paradox. Knowing how small we are makes what we've accomplished even more remarkable. We're tiny. We're brief. Our entire species has existed for a few 100,000 years, which is 0.01% of the universe's age. We've had modern science for maybe 400 years, which is 0.03% of cosmic history. And in that eye blink, we measured the universe. We counted the stars. We understood our place among them. That's what this story has been about from the beginning. Not the number itself, though. 200 billion trillion is certainly impressive. But the journey to get that number, the human capacity to ask questions like, how many stars exist? And then spend centuries developing the methods and instruments needed to answer them. We're not content to simply experience the world. We build tools to see farther. We develop theories to understand deeper. We ask impossible questions and then figure out how to answer them. This is what makes us human, not our physical form, not our evolutionary history, but our capacity for understanding, our ability to grasp concepts far beyond our immediate experience, our drive to measure, to know, to comprehend. We're matter that became conscious of itself. We're the universe's way of knowing itself. Atoms arranged in such a way that they can ponder the nature of atoms. Products of the cosmos, capable of understanding the cosmos that created them. From one small planet, we reached across billions of light years and counted stars. We measured galaxies at distances so vast their light has been traveling for most of the age of the universe. We calculated the total stellar population of everything we can observe. And that brings us to the final question, the question this entire journey has been building toward. What does it mean? What does it mean for you personally that 200 billion trillion stars exist in the universe? You are one person on one planet, orbiting one star among 200 billion trillion stars in the observable universe. From a cosmic perspective, you're insignificant. Your planet is a speck of dust circling an average star in an unremarkable region of a typical spiral galaxy. Your location is utterly ordinary. There's nothing special about where you are in space. Your civilization has existed for maybe 10,000 years, if we're generous, counting from the first agricultural settlements. Modern industrial society is only about 250 years old. We've known about other galaxies for barely 100 years. We've understood the true scale of the universe for less than a human lifetime. Human civilization represents about 0.07% of the universe's age. That's 7/10 millionths of 1%. If the universe's history were compressed into a single year, all of recorded human history would fit into the last 3 seconds before midnight on December 31st. You're tiny. You're brief. Your entire species is a momentary spark in cosmic time. The universe existed for 13.8 billion years before you appeared. It will continue for trillions of years after you're gone. You occupy an infinitesimally small slice of space and time. Your problems, whatever they are, occur on this one small world. The argument you had yesterday, the deadline you're worried about, the relationship that ended, the job you're trying to get, all of it happens on one planet among 300 billion trillion planets scattered across the cosmos. The universe doesn't notice. The stars don't care. 200 billion trillion nuclear furnaces continue fusing hydrogen into helium, completely indifferent to your struggles. Galaxies collide and merge unaffected by your existence. The cosmic web continues evolving, oblivious to your concerns. From that perspective, nothing you do matters. You're a brief arrangement of atoms on an insignificant world, destined to disperse back into the universe within a few decades. You're temporary local and cosmically irrelevant. But here's the other side of that truth. You're also extraordinary. You're matter that became conscious of itself. Your atoms arranged in such a precise way that they can think about atoms. You're the universe's way of knowing itself. You're a piece of the cosmos that became aware, that developed the ability to look outward and understand what it sees. That's remarkable. That's extraordinary. That's actually unprecedented as far as we know. In 200 billion trillion stars, we've found no evidence of other conscious beings. Maybe they exist. Probably they exist somewhere, but we haven't found them yet. You might be one of the rare arrangements of matter in the universe capable of understanding the universe. That capacity, that ability to measure and comprehend and grasp concepts far beyond immediate experience, is what makes you special. The paradox is beautiful. You're tiny and brief, but you're capable of grasping immensity. You exist for maybe 80 years on a planet 8,000 miles in diameter, but you can understand structures spanning billions of light years. You can measure galaxies so distant their light has been traveling since before Earth existed. You can look up at the night sky and know what you're seeing. You can calculate distances to objects you'll never visit. You can count stars you can never see individually. You can comprehend, at least intellectually, numbers with 23 zeros. Every photon that enters your eye connects you across space and time to distant stars. When you look at Sirius, the brightest star in the night sky, you're seeing light that left that star 8.6 years ago. When you look at Betelgeuse, you're seeing light that departed 550 years ago during the Renaissance. Ancient photons traveling through the void for centuries, completing journeys measured in hundreds of years just to enter your eye and be absorbed by your retina, creating the sensation of seeing a star. You're connected to those distant suns through light, through physics, through the shared material of atoms that were forged in stellar cores billions of years ago. The oxygen you're breathing right now was created inside massive stars that exploded as supernovae before the sun existed. The calcium in your bones came from dying stars. The iron in your blood was synthesized in supernova explosions. You're made of processed stardust, the ashes of stellar generations that lived and died so you could exist. You're not separate from the cosmic story. You're part of it, made by it. You're stardust that became conscious enough to discover its own origins. This perspective can be humbling. Your problems really are small in cosmic terms. The things you worry about happen on one planet that's invisible from even the nearest stars. Your concerns are temporary and local, but this perspective can also be freeing. You don't carry cosmic significance on your shoulders. You're allowed to be small. You're allowed to have small joys and small sorrows. You don't need universal importance to matter. You matter to yourself. You matter to the people around you. You matter to your community, your family, your friends. That's enough. You don't need the universe to care about you for your experience, to have value. Your problems might be small in cosmic terms, but they're real to you. The universe doesn't care if you miss your deadline, but the people who depend on you do. The stars don't notice your heartbreak, but you feel it, and that feeling is real and valid. The cosmic perspective doesn't diminish your experience. It contextualizes it. You're part of something vast and ancient, but you're also here now, experiencing this moment, having this particular life, with its particular joys and struggles, understanding the scale of the universe. Knowing that 200 billion trillion stars exist doesn't make your life meaningless. It makes it miraculous. Against all odds in a universe that's mostly empty space and dead matter, you exist. You're conscious. You're capable of understanding. You're living during the epoch when stars still light up the sky. You're here during the billions of years when the universe is bright and active and filled with stellar light. You're experiencing existence during one of the most magnificent eras of cosmic history. You're lucky. You were born on a planet with liquid water and a stable atmosphere, and a moon that creates tides, and a star that provides steady energy. You exist during a time when your species has developed the tools to measure the universe. You live in an era when we know how many stars exist. That combination of circumstances, that precise arrangement of space and time that led to your existence, is unlikely to the point of being nearly impossible. But it happened. You are here, and that's extraordinary. Understanding your place among 200 billion trillion stars doesn't make you insignificant. It makes you part of the grandest story ever told, the story of matter and energy evolving over billions of years, eventually producing stars and planets and life and consciousness. You're a chapter in that story. A brief chapter, yes. A small chapter in an incomprehensibly large book. But you're here. You're experiencing it. You're part of the universe becoming aware of itself. And that brings us to one final thing, one last thought to carry with you. Tonight, when you walk outside and look up at the sky, you'll see a few thousand stars scattered across the darkness. Maybe 2,000 if you were in a city with light pollution. Maybe 4,000 or 5,000 if you're somewhere truly dark. Remember what you now know. Those visible stars are the nearest neighbors in a population of 200 billion trillion. For every star, you can see there are 50 million invisible ones swimming in the darkness beyond your perception. Each point of light you see is a massive nuclear furnace. Each one is fusing hydrogen into helium in its core, releasing energy equivalent to billions of nuclear bombs detonating every second. Each one has probably been shining for millions or billions of years and will continue for millions or billions more. Each star likely has planets, rocky worlds close to the star, gas giants farther out, ice worlds in the distant reaches of each system, moons orbiting those planets, asteroids and comets filling the space between. Each star is probably the center of its own system of worlds, each world with its own geography, its own geology, its own story. Some of those worlds might have life, simple bacteria in underground oceans, complex ecosystems under alien skies, maybe intelligent beings looking up at their own night sky, asking the same questions we're asking, wondering if they're alone. The light entering your eyes has been traveling for years, or centuries, or millennia to reach you. The photons you're seeing left their source stars long ago, crossing the vast distances of interstellar space, finally completing their journey by striking your retina. You're seeing the past, the stars as they were years ago, centuries ago, when that light began its journey toward Earth. You're looking back in time with every glance at the night sky. We measured this. We counted them. We understood our place among them. Let's recap the journey we've taken together. We started with a simple question. How many stars exist? Your brain couldn't process the answer at first because it wasn't built to handle numbers that large. We had to teach ourselves to feel the difference between millions and billions and trillions using time as a measuring stick. We discovered that the 4,000 stars visible on the darkest night represent less than 0.002% of the stars in our galaxy alone. The night sky is a lie, showing us only the nearest neighbors while hiding the vast majority in darkness. We followed Edwin Hubble's 1923 discovery that shattered our understanding of the universe's size. Andromeda wasn't a nebula in our galaxy. It was an entire galaxy of its own, containing hundreds of billions of stars. We learned about the Hubble Deep Field, that photograph of seemingly empty space that revealed 3,000 galaxies in a patch of sky smaller than a grain of sand held at arm's length. We extrapolated from that observation to arrive at roughly 2 trillion galaxies in the observable universe. We did the math. 2 trillion galaxies times an average of 100 billion stars per galaxy equals 200 billion trillion stars. 2 followed by 23 zeros. More stars than grains of sand on all of Earth's beaches. More stars than seconds have elapsed since the Big Bang. We explored what stars actually are. Nuclear furnaces fusing hydrogen into helium, converting mass to energy shining for millions or billions or trillions of years, depending on their size. We learned about red dwarfs and yellow dwarfs and blue giants, about binary systems and stellar remnants. We discovered that planets are common, that most stars have worlds, that the universe might contain 300 billion trillion planets scattered across the cosmos. We contemplated the possibility of life on some of those worlds, and the puzzle of why we haven't found any evidence of it yet. We learned that you are made of stardust, not metaphorically, but literally. Every atom in your body, except hydrogen, was forged in stellar cores billions of years ago and scattered into space when those stars died. Your recycled star material, the universe made manifest in conscious form. We saw how stars organize into the cosmic web, creating structures of filaments and voids across billions of light years. We witnessed galaxy collisions and mergers. We learned that star formation has peaked and is now declining, that we live in the twilight era of the universe after the golden age has passed. We understood how we measured all this using the cosmic distance ladder, building from parallax to Cepheids to supernovae to redshift, each technique extending our reach farther into the cosmos. We appreciated the achievement of humanity in measuring the universe from one small planet, and we arrived at the final insight: you're tiny and brief, but capable of comprehending immensity. That capacity for understanding is what makes us human. You are the universe looking back at itself. Your stardust arranged in such a way that it became conscious, that it developed the ability to measure and count and understand. You're a piece of the cosmos that became aware, and that's the most miraculous thing of all. The next time someone asks you, "How many stars are there?" you can tell them, "More than you think, much more. 200 billion trillion in the observable universe, with possibly infinitely more beyond our cosmic horizon." But the real answer isn't just the number, it's what that number represents. The vastness of the cosmos, the incredible diversity of stellar types and evolutionary stages, the possibility of countless worlds and perhaps countless forms of life scattered across incomprehensible distances. It's the story of how we figured it out, how we built the tools and developed the techniques to measure the universe from one tiny world. It's the reminder that we're both insignificant and extraordinary, both tiny and capable of grasping infinity. 200 billion trillion stars, each one a sun, each one potentially the center of its own system of worlds. each one a nuclear furnace, fusing elements, pumping energy into space, possibly fostering life, definitely contributing to the ongoing evolution of the cosmos. And from one small planet orbiting one ordinary star in one typical galaxy among 2 trillion galaxies, we counted them all. That's what makes us human. That's what makes this moment in cosmic history special. We're here. We're conscious. We've grasped the magnificent scale of the universe we inhabit. That's why tonight, and every night after this, when you look up at the sky, you'll never see it the same way again. You'll see those few thousand visible stars, and remember the 200 billion trillion hidden beyond them. You'll see photons that have traveled for years or centuries to reach your eyes. You'll see nuclear furnaces scattered across space, each one potentially surrounded by worlds, maybe some with life. You'll see the universe, and you'll understand your place in it. Look up, remember, wonder. The cosmos awaits.